Much like with the electric field, we will find it convenient to divide out the charge used to map the electric potential energy. That is, we'd like to have a function that represents the influence of source charges without regard to the charge we're using to test it. This is exactly analogous to how we would take the forces and divide out the charge to get the electric field. We call this new thing the electric potential and symbolize it usually with V. V is defined as the limit as the test charge becomes small of the potential energy of the test charge over the test charge itself. That means the potential is the electric potential energy per coulomb. The unit for it is something called the volt, which is just 1 joule per coulomb. Volts will come out being kind of really important for us to keep track of, and you want to always be able to come back to the idea that it's defined as a joule per coulomb. Note the word linguistics here. It's the potential. It's not the potential energy, or indeed the potential anything. In English, potential is an adjective and is usually followed by a noun. But in physics, for whatever reason, it's not. It was just a choice of language that was made a while ago, and it's not the best choice of language, but it's the one we're really stuck with. It's woven into a lot of what we do in physics and engineering now. All right, if we've determined the potential for a particular collection of source charges, we can then find the energy in the system when a new charge Q is present by saying U equals Q times V. The potential is a feature of the source charges, but has no physical expression until a new charge is present. This is sort of like saying that the potential energy, gravitationally, is the mass times something. Now we know that the something is really GH, and so this is the gravitational potential. And you might wonder, well, why? Who needs that? Why'd they order it? But the point is to say, G and H are a feature of the Earth, the place you're on, whereas your energy is a function of that, but also of your own mass. So there's sort of setting the stage, and then there's sort of the actors. And here, V might be set by setting the stage, having a bunch of other collections of charges and so on out there, and then we want to see how they influence new things. So you might talk about getting you might have a pair of charged plates, and then you fire an electron beam between them, and you're really interested in what the beam of electrons are doing, so you would just say their energy is Q times the V that they have there. Textbook is kind of fond of saying you've got some charges and they make these wavy, spooky things. They're trying to indicate that there's some influence, some region of distortion of space-time. All right, they alter the space-time around them by creating electric potential, and it's independent of anything except those charges. And then if we put a charge in that potential, it has this energy, which is Q times V. Important things about potential. If the potential is increasing, then a positive charge slows down. If potential is decreasing, a positive charge speeds up. And negative charges do the opposite. They slow down when they enter regions of decrease in potential, and they speed up when entering regions of increase in potential. We often summarize this by saying positive charges fall down or accelerate down potential gradients. They roll downhill. Electrons, being negative, act weirdly. They kind of roll uphill. And we'll see that this is something more than just metaphorical in a little bit. In this figure, a little bizarrely, this is the low potential and this high potential. So potential is going from high to low. Positives go from high to low potential, so they accelerate this way. But negative charges go from, and then positive charge, on the other hand, trying to head up the potential, gets slower. Again, thinking about an analogy to the hill, a positive charge, when it rolls uphill, gets slower. Just always keep in mind that negative charges, which are sadly most of the ones that are moving, do the opposite. But you can get away without worrying about that for most of electrodynamics. So, a proton is released from rest at the dot, and after what happens to the dot, where someone has told us that the potential in this region is plus 50 volts here, and relative to this one, which is 0, and this is 50 volts lower. Well, we know that positive charges roll downhill, i.e. they move down potential gradients, so the thing is going to want to go that way. So that's out, and that's out, and that's out. And then the question is, well, what happens to its actual speed? But we know that it accelerates down potential gradients, just like a thing rolling downhill. If a positive charge is released from rest, it moves in what direction? and they say a stronger electric field or a weaker electric field does move, or higher electric potential or lower electric potential, or a combination of a weaker field and a lower potential. And this is kind of going to tempt you because you're like, well, what electric field tells me is which way it accelerates. So if I have that as my charge, and I have somebody told me there's an electric field, say, pointing this way, well, it would move in the direction of the electric field, but it doesn't matter if that field's getting stronger or weaker. Put it in a different way, if we have very strong field and then a weaker field, that's case 1. Or we could have a relatively weak field and then a much stronger field. In both cases, the particle moves along the field line. It doesn't really matter that it's going towards or away from a stronger or weaker field, just that it moves along the field line. So neither of these things are actually valid. In fact, we know that positive charges roll down electric potential, so it's D.